All right. Good morning, everybody. Welcome to the last week of DSCI 512 and other courses in this block. In this week, we are going to be talking about optimization. So today we're going to learn about a particular optimization algorithm which is well suited to a particular type of problem. And in the next lecture, we're going to cover another technique. And both of these techniques are going to be used by you during the lab for the lab exercises. Okay. So what's optimization? Optimization is when we want to find the maximum or minimum value of a function or a set of values that we have in a data set. So we have already seen examples of this, of optimization in general. What is one example that you can remember from previous lectures? Yeah, exactly. So finding, for example, the maximum value inside a list or inside any other data structure, like a list. And also, we have also seen that depending on what that particular data structure looks like, the optimization process could be improved in some cases. For example, if we have an unordered list, we have to go through everything to find the maximum value, for example. Or if the list is sorted, then we might be able to eliminate some of the values inside of that data set and then only consider the ones that are relevant. So we know in advance something about the structure of the problem that we can use to our own benefit. Okay, so that's just one relatively simple example of optimization, but most real-world examples of optimization that are of practical importance are usually more involved than that. So, in your machine learning course, you have been working on like objective functions and stuff like that, right? Or no, not yet? Okay. So all of the supervised machine learning techniques that you're probably impatiently waiting to learn about, they all depend on this optimization process, and they all essentially boil down to finding the best values for a set of unknown parameters. So again, you can see that even in that case, that whole area of supervised machine learning is going to be about optimization. So let's get started with this, with the course. With the lecture, and let me show you or talk about a couple of examples that we can have in the context of optimization. So there are two cases that we're interested in when we're talking about optimization. One is continuous optimization, the other is discrete optimization. For example, you are all familiar with functions like this, so fx, x minus 0.9 raised to the power of 2, and then you want to find the point at which, for example, this function is minimized. And from elementary calculus, we know that we can set the derivative to 0, and it's a cup-like function, and then we can find the minimum by an analytical solution, basically. And in that case, we find the minimum to be x equals 0.9. That's the point where the minimum happens. However, if this was a discrete optimization case, we would be only allowed to choose integer values for x. So in that case, the best value that could have minimized this function would have been x equals 1, and the minimum value would have been 0.01. So there's this distinction between the two cases. What we're usually most familiar with is the continuous case. However, in today's lecture, we will be talking mostly about the integer scenario where the variables are integers. Okay. All right, before going into that, there is another category of problems that are called linear problems with optimization and nonlinear problems in optimization. So this problem that you can see over here is an example of linear or nonlinear. Yeah, it's not a linear function, so it's a little bit more complicated in order to see where the minimum or the maximum value happens. And the nonlinear case is usually what we're interested in when we are talking about optimization in the context of supervised machine learning. For example, in your DSCI 572, supervised learning 2, when we're talking about neural networks, we have a complex machinery that we want to put to work in order to understand the patterns in the data. And then inside of that particular machine that we're building, we have a lot of unknown things. And basically what we want to do is to tune all those unknown things in order to fit our data the best way possible. So in that case, those values are continuous, and that'll be an example of continuous optimization. So we will talk extensively about that in DSCI 572. However, here in this case, in today's lecture, we will be mostly dealing with linear optimization. But before that, let's get started with an example exercise. And I use this in order to tell you about the terminology that we use in the context of optimization problems. Before that, if you happen to have pulled from the repo in the past 2 days, please do that again today, because I've made a couple of number of corrections to the lecture 7, so that would be a good idea to do that now. All right, so example problem. Okay, so find the length 8 string of letters, for example, strings such as these ones that we can see over here, that contains the most English words in it. Okay, so in this case, because we're dealing with a discrete optimization problem, we can count how many possible situations we have in order to characterize our search space. And a search space is the space of all possibilities where we look for the minimum of the maximum value. Okay. So here, for each place in that string, we can use 26 lowercase letters, and because we care about the order of those letters and because we can repeat those letters, we have 26 to the power of 8 possibilities. Okay, so that's the space of possibilities that we want to basically investigate in order to find what are the data points that we like, what are the data points that basically maximize this whatever output we have here, and we'll talk about that. Okay, so let's compute this value. This is the total number of basically data points that we have in this space of possibilities, which is a huge number. Yeah, I guess, yeah, so billions, or no, trillions. So that's a lot. Bottom line is that is a lot of numbers, a lot of possibilities. So the thing is, if we start generating all of those values and start looking through them one by one, we have to consider a lot of possibilities, all of these. Okay, and that method is called, by now we know that this method is called a brute force method. So basically enumerating all possibilities, going through them all, inspect each one of them one by one, and see if that fits the criterion that you have in mind. Okay. All right. So let's now talk about how we can specify an optimization problem and use it for this example problem that we have over here. Well, we need a few things, a few ingredients. So first of all is the space of all possible inputs, something that I verbally discussed here. So we have these letters, each position can take on 26 alphabet letters, and so on and so forth. We also need to have an objective function, meaning that there is some criterion that I want to look at, and based on that, I want to judge whether this particular data point fits my criterion, is a good choice for the optimization or not. So that's when we define an objective function. This objective function sometimes is also called a cost function, just so you know, but here in this lecture, in this course, we use the term objective function. And also we need to know whether we are maximizing something or minimizing. Okay. Any questions so far? So for the example that I just showed you, this example with 8 letter string, the space of all possible inputs is all 8 lengthed strings, which we know that we have this many possibilities over here. And the objective function is the number of English words in the strings. So which one of these particular data points, which one of these 8-letter strings contains the most English words? That will be the value that maximizes our objective function, basically. Okay. So let's get started with this example using the brute force method. Okay, so here I'm using a dictionary that contains the 1,000 most used English words, not all of English words. So just the first most used one, the first 1,000 most used words. So download that. Okay. And then I'm going to define this function over here. English words in string, which basically does something really simple. It just looks through the string, consider all substrings, all possibilities, and then checks whether that substring exists inside of that list of words that we have. Okay, so pretty simple. The code is not that important here, but just so you know, we have a for loop starting from the beginning of that string, and then we have an inner for loop for the end. So we start from the first letter. We say that, okay, is this an English word? 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 And then we check all the possibilities. Then we move on to the next character, and then we do the same thing again. Is this an English word? Is this an English word? Is this an English word? Something like that. So all the characters. Okay. So as a practice, what do you think the time complexity of this function is if the length of the string is n? O log n? Okay. O log n. Okay. O of n. N log n. Okay. O of n. N squared. N cubed. Okay. No, that's good. Okay, that would be n squared, because we have an outer loop and an inner loop, and then these two operations. So when we check whether this exists inside of that word list, would be a constant time operation, this one and also this one, both the checking and addition, because this is a set, and this one, and basically we have also discussed this when we have a for loop that runs n times here, but here we have a bunch of terms like n minus 1, and then n minus 2, and then n minus 3. That would be an arithmetic series, and when we multiply this by n, we will still get n squared. Okay, but that's not important detail here. So again, the purpose is that we have this function, we apply it on the string, and we find the number of English, the English words inside of that string. So let's run that, and then English words in string the apple, and these are the words that it finds. So a, apple, he, and the. Okay. All right, so now let's discuss the objective function here. So what was the objective function that we want to optimize? Basically, that's the number of English words. So we already have defined this helper function that finds the English words, and then we want to check out what is the number of that. We could have packed the two together inside of one objective function, but I mean, either way, it'll be fine. So length of that particular set that we have, the size of that set. So if we apply the same thing onto the apple string, it says 4. So we have four English words inside of that string. Okay, if we proceed like that, the code will be too slow if we consider all of the English letters inside of that string that we're searching for. So we only consider the first 5 letters of the alphabet, meaning A, B, C, D, E, so that we can run the code in reasonable time in the lecture. Okay, so in this case, we will have this many possibilities, around 400,000 possibilities. In the previous case, it was way more than this. Okay. Now, I have the code here from Lab 2, which is a function that you give it a bunch of letters, and it comes up with all of the length and strings that it can make with that particular collection of letters, basically. So the code is the same, again, similar to Lab 2. The details are not that important here. What it does is the most important thing. So we get some inputs, a number of letters, and then we say, okay, we want all of the combinations of those letters with that you can make strings of size 8 out of that. And then if you look at that, it gives you something like this. So yeah, repetition is allowed, and then, yeah. Okay. So now, what we can do is that we can basically go through the entire data set and then check the number of English words in each data point, in each string, and then see, and then keep track of things. Okay, is this the largest one? Is this the largest one? Is this the larger one? So that's the thing. So what I'm doing here is that I'm mapping this objective function onto the list of inputs. So this map is nothing too complicated. It just takes a function, applies it onto every element inside of a list. Okay, because if you just directly apply the objective function on inputs, it won't work. Okay, and then I just list all of the possibilities here, convert it to a list, and then compute the max score. So it takes a few seconds, okay, and it tells me that the largest number of English words in the strings that we have is 5 for this particular data set. Now, we can also see what was the string that actually led to this result. It was this string. Okay, and you can already see some English words inside of that. For example, bed or dad or add. Okay, and we can retrieve those. Let's see, okay. So these are the 5 English words. Okay, now there were 400,000 strings, and imagine going through that by hand, or if you have many more possibilities like that, yes. Good question. Yeah, the question is that the only string with 5 English words in it? No, the solution is not necessarily unique. We might have a bunch of such strings that contain 5 English words. I think it returns, I don't know the first or the last, but one of those possibilities. I have to check. Yeah. And okay, and basically one other thing that we can do is that to sort the list, and then check the items happening at the end of the list, and get all of them. Pardon me? Mm-hmm. Looks like it, yeah. Mm-hmm. Yeah, good point. Okay. And again, yeah, this is, again, something that we just discussed. There are, seems like a bunch of 8-letter strings that have 5 English words in them. Okay. All right. So one thing here is that for this particular problem, we need to do this brute force method. As far as I know, there's no other solution, although there might be something else that we could do, for example, with the probabilities of some letters coming after other letters. Yeah, something fancy might be possible to be done there, but at least right now I don't know of an algorithm that actually solves this problem better than a brute force search. Okay, and this is mostly because there is no, at least, apparent structure to the problem. It is no easy way to say, okay, if I get this particular string in this particular position, this particular word in this particular position, then I'm gonna get another word like in the next 2 indices. It's not possible to come up with an idea like that. So it's kind of like noisy, and it's kind of like unstructured. Okay. Now, another example that we can think of in terms of optimization is finding the shortest path between 2 nodes, like A and B in a graph, and we discussed this, that we can use something like the BFS algorithm to do that. Again, another instance of optimization. And for that case, the possible inputs are all of the paths that we can take from A to B, objective function, obviously the length or the distance, and we're trying to minimize that. Okay, just another example. Okay. Right, just like I mentioned, again, the easiest way to solve optimization problems is brute force. But brute force is not a feasible method in most real-world practical applications. So I can give you an example. In the example with the parabola thing, so if you want to find this minimum value, to do what would be a brute force method to find that value? For example, if I limit myself to here and here, x equals minus 5 and x equals 5. Exactly, so I have the f of x here, okay, and I can start from here and then make very small intervals and then compute f of x on that, keep track of things until I reach a value that's the smallest value in there. That will be brute force. And you can imagine that, okay, here this is reasonable. If you go into multiple dimensions, then imagine producing squares or cubes or hypercubes containing all of those data points, and that grows exponentially. So brute force is not feasible in that case. Okay, but as we can see here, there is some structure to this problem that we can take advantage of, and we will do exactly that. Okay. So again, this is just another point here that this was a case of 8-letter strings with 26 alphabetic letters, and I will actually show you, I can show you how long it takes to do that actual scenario with 26 letters. So let's just as a practice maybe do that. Okay, we can, for example, take this objective function and do a time it. Okay, I just want to see how much time it takes to run that objective function on maybe one input value. Or let's do that. Okay. Oops. Let's see. So that's subscribable objective function. Inputs. Okay. Yeah. Okay. So let's see how much one operation takes. Okay, 6 microseconds, and we saw that with the 26 letters, we had this many possibilities. Where is it? Yeah, this many possibilities. So if I multiply this 26 raised to the power of 8, and then this is the number of data points that I have to check. For each one of them, we take 6 microseconds, and then we want to divide this by 3,600 seconds in an hour, and 24 hours, and and 30 days, and 12 months. Is that correct? Okay, so it takes this much time, which is 0.04 of a year, in order to compute that value. Okay, so this is, this is not doable, definitely. Okay. All right, now let's talk about constraints for a few minutes. So far we only had an objective function, a set of data points, and we want to compute the maximum or minimum value for that objective function where it happens in the data set. Now, for most of the problems, we actually also have some constraints, because in real world, for example, resources are limited. We want to take that into consideration in our problems. So, for example, in the all length 8 strings, such that each letter appears at most twice, that would be a constraint. So in the previous case, we had a bunch of letters that would be repeated no matter how many times, but we can put a constraint on that. So we only want to consider the possibilities where each letter only considered twice. That would be a constraint. Okay, and for example, something like this, A, and then B, that violates the constraint because there is more than 2 appearances of the letters A and B. Okay. So to specify an optimization problem, coming back to what I discussed before, we need to specify the space of possibilities, the objective or scoring function to measure how good each value is, and then possibly a set of constraints which takes an input and returns true or false, whether that particular data point satisfies that particular constraint, and if we're maximizing or minimizing. Okay, we just added this third statement here. Okay, so here, this function, character appears at most twice, so this is an example of a constraint. So it basically just, it doesn't matter how the code is written, it just matters if it gives us the right results. So for example, if you run it on this example over here, it says that whether this character appears at most twice, it says, yes, true. That is true. Okay. So a bunch of assert statements. Okay, and now this was the data set before. And now if we regenerate that data set for when we have constraints, we can see that the original length of the inputs was around 400,000 data points, and now we only have 63,000 because a lot of those data points didn't satisfy that constraint. And what's the importance of this is that we're eliminating, if we are careful, not in this case, if we are careful, we can eliminate a lot of possibilities in advance and then search through the remaining space of possibilities. This is usually what makes a lot of algorithms much more efficient. An example of this would be the binary search thing. So because you knew that there were a lot of possible data points that didn't really work for us in each step, we just threw them away. And then by using that, we could have obtained a O log n time complexity for our search instead of O of n. So again, there was this structure, and there was this constraint to our problem. Not exactly constraint, but something that could have limited our search space, and we used that. Okay, if we check the first 10 elements here, we can see that, yeah, there are no letters that are repeated more than twice. Okay. So now let's run this again on the constrained inputs, and now it says that the maximum number of English words occurring in a string is 4. So you can see that that optimum value changed because we have applied a constraint in the space of possibilities actually changed. Okay, let's see what that string is, or one of those strings is. So you can look at here. Okay, yeah, 4 choices here. All right, any questions about this example? Yes. Yeah, that's a good question. So yeah, the number of English words in that string goes down. That's true, and you say that it might be a bad thing for the optimization, but that has been done according to an external constraint that was imposed on us. That wasn't like something that we could control. So we say that, okay, based on that particular constraint that we can't really change, this is the optimum value that you can get. It's like something like, okay, you have this much money in a department, and you want to spend it as wisely as possible on the things that you want to buy for the department. So there is that constraint. We can't really do, we would have wished to have all the money in the world, but that's not the case, so it limits the possible. Kind of, yes, that's right. Yeah, these are not the same problems, yes. Any other questions? Okay. Yeah. No, it doesn't mean that, no. It just, again, it just limits the search space based on the external, basically, limitations that we have. All right, so you can read through that later. It's just something that I've mentioned verbally in form of text here. Okay. Okay, for the rest of this lecture, we will be working on an interesting problem actually, which is the TA assignment that we have to deal with every year with MDS. And it's the problem of, so we have a bunch of people that sign up to be TAs for MDS, and then these people have different preferences for the days that they can work with us, the kind of courses that they're interested in, the kind of courses that they're enthusiastic about to teach, and so on and so forth. So we have, again, a problem that we have limited resources. For example, we know that a TA can work at max, let's say 10 hours a week. Those are like the external constraints. And we also have some variables at play that we want to, for example, in this case, we want to maximize the TA satisfaction so that if we can assign as many courses as possible that they're enthusiastic about, okay? And actually, in a smaller scale, I deal with the same problem when I want to assign different parts of the work related to a single course to different TAs in the course. And I have to consider, okay, how much time each TA spends on grading, on coming to the labs, and each TA has a different preference for the days to come to the labs. Some TAs enjoy some people enjoy attending the labs, some other people are more comfortable grading. So it's when you start doing that by hand, manually, you'll quickly realize, even with a very small number of TAs and possibilities, it's very hard to do this in an optimal way, manually. The situation is similar to trying to solve a Rubik's Cube. So when you're about to figure out the last move that is seemingly the best move, you make that move and you mess up the whole thing again. It's exactly something like that. So we don't want to consider those decisions separately from each other. We want to consider all of them together. It doesn't make sense at this point, perhaps, but we will go through this example and we will see how we can solve this problem using algorithms that are designed to solve this problem. Okay, let's get right into it. All right, so here is the TA applications. And we have, so the names are from TAs from the previous cohort. Okay, you can see that each TA has certain days of availability, Monday, Tuesday, Thursday, and there are some levels of competency or proficiency for R and Python, and the courses that people are okay with teaching or TAing for, and the courses that they're enthusiastic about. So that's the TA data set that we have. And we also have a number of courses. Okay, so these are the courses, and then the blocks in which these courses are taught, the primary languages, and the lab days for those courses. All right, let me just run these. Okay, so the goal is to match TAs to courses so that our staffing needs are covered in the best way possible. And by the best way possible, we want to maximize the number of assigned courses that TAs are enthusiastic about. Okay, so here are the constraints that we have. Each course should be assigned exactly 2 TAs. We need that to happen. Okay, in reality, it's more than that, but in this case, let's say that it's 2 TAs. A TA can only cover one course at a time in each block. Okay, so it means that they cannot TA for 2 courses in a block or more. And a TA can be assigned to a course that they have listed as can teach or enthusiastic to teach. So we don't want to assign people to the courses that they haven't listed already in the can teach or enthusiastic to teach list. And finally, to cover a course, a TA must be available for at least one of the 2 lab days. Okay, and this doesn't guarantee lab coverage, but for simplicity, we consider that to be the case here. So we have these constraints. We want to maximize TA satisfaction, and we have the data sets. Now, the activity here for you to appreciate what's coming next is to try to do this manually. Okay, so just consider that you're the TA managers in this department, and you want to do this task by hand, naively. Okay, so again, the 2 data sets are here, and try to see how many TAs you can get for the courses that are actually enthusiastic about teaching that course. Okay, so bring out your pens and papers and let's try that for 5 minutes and see what happens. Yeah, you have to clone the report, pull the new data. Yeah. Okay, the break starts now, so feel free to continue doing this if you want, but otherwise you can take a break, and then we'll be back in 5 minutes. Okay, any luck? Anybody figured out just maybe a solution, not the optimal one? And this is, consider that this is a relatively small problem. Yeah, I mean, the constraints really mess with you. They don't allow you to, so as soon as you start moving stuff around, then okay, the things that were working in the beginning, now everything, you have to change everything again. Exactly like the situation in solving a Rubik's Cube. Okay, so it means that this kind of sequential decision making doesn't really work here. We have to consider everything together, and we have to have a strategy for that. And yeah, I knew that this is not possible to do by hand, and not even the optimal solution, even finding a solution that works and satisfies all the constraints is really, really hard. Okay, now let's see what we can do. Okay, so there's a difference again between a solution and the optimal solution. A solution is something that satisfies all the constraints. It's not the best possible solution. So we can actually go ahead and distribute the TAs between the courses, but it's not guaranteed that we can make them all happy or most of them happy. Okay, it might be possible to do that. That's a solution. It satisfies the constraints, but it doesn't make everybody as happy as possible. We want to do that. Okay, so let's start formulating this problem, and we go through a bunch of questions that we have to ask ourselves, and then we answer those questions using code. Okay, so in this problem, we are trying to maximize something, that is the TA's satisfaction or happiness. So there is this package that we will use in this course, in this lecture, that is called PULP. It's Python linear programming. I don't know what the U stands for. If you know, please let me know. Okay, we use this package. I have imported it at the top of the lab, and this allows us to solve problems of this kind. And why is this a particular package rather than using SciPy or NumPy or stuff like that? This is because these kinds of problems are linear, meaning that all of the constraints that you work with, the objective function, those are all linear, meaning that we have something like x1 plus x2 minus x3, and then the constraints are x2 plus x50 plus x20 greater than 1, something like so. All of the constraints and the objective function itself, they're all linear. And when everything is linear, we call this problem a linear programming problem. And the programming in this name does not have anything to do with computer programming. It's about planning. It's about scheduling. Okay, so you can think of it as linear planning or linear scheduling, meaning that you have a problem of scheduling or planning that is linear. Okay, so it doesn't have anything to do with computer code, although we use code to solve that problem. So this is why it's called an LP problem, linear programming problem. So I'm just going to show you the syntax here. This is how we define a problem object using this package. Why is it defined like this? Because the developers have decided to do so. Okay, we have to specify a name for that. That's just the name of the object so that we can an identifier. And then we have to specify whether we are minimizing or maximizing, and we can use this syntax to do that. Okay, so let me run this. Now, we have to set up the variables that we want to have. And we call these variables decision variables. What are decision variables? Okay, so when you were working on this problem, you might have thought that it would be a good way to start tabulating the results of your assignments. So we can tabulate the variables. Okay, this TA can potentially TA for these courses. This TA can potentially TA for all of those courses if we don't have a constraint. Okay, and we can think of all of these places as binary variables. Okay, so I can say that, for example, I have a variable x of Chris and 5 to 1. That will be this element here. If that value is 1, it means that we have assigned Chris to TA for 5 to 1. If 0, it means that we haven't assigned that person to TA for that course. So in this case, we have 12 TAs. Yeah, 10 TAs and 12 courses. So how many variables will we have in this case? So 10 TAs, 12 courses? Right, yeah. We will have 120 variables. Okay, and that was part of the reason that you weren't able to figure this out. 120 variables, meaning that you're working in a 120 dimensional space, and yeah, let's just leave it at that. Okay. Now, inside of this pulp package, I have to somehow let this pulp recognize my variables, and there are various methods to build your variables, but this is one method that creates dictionaries for each variable so that we can access those variables easily. And again, there's nothing really crucial about the syntax. This is just the way it works. So we are defining a variable called x. This is just the name. And then for the names of each one of those variables, this is the starting letter or character. And then we want to have, for example, x Chris 511, x Chris 551, and it takes all of those values from the list of TAs. Okay, I can print TAs for you here. These are the list of TAs. Okay, and then we have a similar list called courses. So it just creates the cross product of all of those. Okay, so let's do that. And each variable looks something like this. So x of Chris 512, for example. It's just and it stores a value of 0 and 1 because we have specified that here. 0 and 1, and we want the type to be integer. Okay, and we have these kinds of variables for all of the TAs and for all of the courses. Okay, and if you check out the type of this, you can see that this is actually a pulp object. All right, now just to give you a glimpse into why this problem is so hard, let's consider how many possibilities could we have. We want to see like how large the search space is. Pardon me? Yeah, consider unconstrained. Yeah, so exactly. So in this case, we have two choices for each place, and we have 120 places. So it's like, okay, it's this many possibilities. That's the search space. Okay, if we have to do brute force, we have to go through each one of those possibilities and check if that maximizes the sum of the satisfactions from all TAs. Okay, and say this one doesn't satisfy, this one doesn't satisfy, this one doesn't satisfy, and then do that for the remainder of the entries remaining in that data set. Okay. With this formulation that we have, it's not efficient, but this is the way that we have to define it in pulp because we haven't defined the constraints yet. Otherwise, in reality, we have 2 TAs per course, meaning that we have 2 spots and 10 possible TAs. And that would be the total number of possibilities would be 10 choose 2 because we don't care about the order of the TAs. So that would be 45 possibilities per course. For 12 courses, 45 raised to the power of 12. So in reality, this would be the number of possibilities we have. And this is way smaller than the actual one. Okay, way smaller, but still, this is a really huge number to search through using brute force. Any questions about the way that we define variables, about the table that I showed you here? Because someone should be confused. It's a lot. I mean, a lot of things are going on at once. Okay, so we can move on. All right. Now let's start setting up the constraints with the pulp language. Okay, I'll start with this constraint over here. So we know that one of the constraints was each course should be assigned exactly 2 TAs. Each course should be assigned exactly 2 TAs. Okay, how can we define this particular constraint in terms of the x's that we have? So we have an x for each TA and each course. Okay, how can we define that? So it means that in each of these columns, which pertains to each course, I want to have exactly 2 TAs, right? What would that be in terms of the x's using this table? Sum of? Mm-hmm. Right. So we want to sum the x's in each column and set it to 2. That would be a constraint, right? I want to say, okay, in this entire column, I just only want to have 2 ones, and in all other columns as well. So we can define that using the pulp's syntax like this. Let's go here. Okay, so for all courses J, we require that the sum of all those J's, meaning that the sum of all those, setting each course as J, for example, course 1, then we just fix J, and we say that then the x's for all TAs should equate 1. Okay, and now in terms of code, this is how we can define it. So for course in courses, just look at this code for a moment. LP sum is the way that pulp understands summing over variables. Okay. And what I'm doing here is that I take each course in the courses for TA in TAs. Okay, it means that for each course, for example, I fix this number over here to course 511, and then I do a loop over the TAs. Okay, and this is a list comprehension, so it creates, for example, X TA1, for example, Amin, Chris, Colby, and then all of those people for 511, and adds them together. Okay, using this pulp syntax, LP.sum. Okay, So I'm going to change it back to courses, and then sets it equal to 2, which is the TAs per course that I have set here. Okay. And the way that we can add this particular constraint to a problem object in Pulp is that we use this particular operator, which is overloaded using the class definitions that we learned about. Okay, so this is just a particular way that this problem object works. If you want to add a constraint, you just take the constraint constructed using Pulp syntax like this, and then add it to problem. That's it. Run this. Oops. Okay. Nope. Course, yeah. Yeah, okay. And if we print this problem object, which is defined using the dunder stir method, you can see all of the constraints added. And this is much nicer to visualize what's happening. So x of Amin, 511, x of Chris, 511, x of Colby, 511, x, and all of that, for all of those 511 values, that should equate to 2, because we want 2 TAs per course. And then the same goes for each other course in this list. Okay, and you can open up the full text here. This is the entire list, and these are these bunch of variables that we have. So each variable is between 0 and 1. Okay, but basically I just wanted to show you the constraints. So we have successfully set up the constraints here. Any questions about the way that we have set up this constraint? Yes. Oh yeah, that's okay. It gives you what's called a generator, but when LPSum works on that, it understands that and converts it to a list so that it can add all those values together. Because otherwise, if you just define something like this outside, you're right. It doesn't give you a list. It gives you a recipe for a list. Yeah, but in this case, it's not a problem. Okay, yes. This one, yes, you can do that. It's just a more concise syntax. Yeah, sure. It's up to you how you construct that, but this is probably a more readable way of doing this. Okay, let's move on. Now, let's see what other constraints we have. Okay. And this is this is talking about how we define the constraints. Okay, just remember that when we add these constraints to the problem, excuse me, actually doing any computation. Okay, it's just defining the problem. And we will see instances of something like this happening in other courses when we just construct the model and then we do something like .fits or something like that that does the actual computation. So at this point, we're just defining the problem. Okay, another constraint. A TA can only cover one course at a time in a given block. Okay, so the way that we can address this is that we take each block and basically do something very similar to the other thing. So we take, okay, for this TA, in this block, I loop over all courses, and I say that this particular value should be equal to 1, because this person can only TA for one course. And we can define it like this. So for J in block, meaning that, for example, we fix block 1 and only look at courses in block 1, and we say that if I do that, okay, this particular TAI, for example, Colby, can, if we add up X Colby for 511, X Colby 521, X Colby 551, that should be equal to 1, because that person is only allowed to TA for one course in that block, just those courses in that block. And then I do the same for the next block, and then for the next TA in block 1, block 2, block 3, next TA block 1, block 2, block 3, I have to do all of that. So this is why here I loop through all the TAs because I want to apply this constraint on all of the TAs, and then I loop through the blocks for each TA. So I take each TA and I just query that course's DF, okay, and this is just the syntax to use the block variable from here. Okay, I say whatever block is this, just plug it in here, for example, block 3. Okay, and then retrieve all of the data in the courses in block 3. Okay, that way I have the courses in that block. Again, the code, how you retrieve those courses in that particular block does not really matter that much. The thing is, we retrieve the courses in that block. That's the important thing. And now I do something similar. So I say, okay, for this TA, this particular TA, make a loop here for all the courses in that block and add them up and set it equal to 0. Set it equal to 1 or smaller than 1, meaning that's 0. So it means that at max, that TA can take for 1 course or no courses at all. Questions? Yes. This one? Okay, so this is a variable object, and it's like a dictionary within dictionary. So it contains all of the variables for our problem. We had 120 combinations between TAs and courses. So each one of those elements it represents one of those binary variables. Okay, and these are actually, you can see them here. X of, for example, Colby and 511, X of Justin and 511, X of Katie and 511, and then the same thing for all the courses. Yes, yes. Each of them is a pulp variable. That's right. Okay. So, any questions about this code over here? Yes. Oh, yeah. The blocks. So I have actually run the code here for the blocks. Let's see. XDF, and that's that. Num entries. Should be, oh no, it's right at the top, yeah. Sorry for the scrolling. Courses, okay. Oh yeah, so this is the list of courses, this is the list of blocks, which is defined as a set. Okay, so we just want to see how many individual blocks, how many unique blocks we have, unique block values. Okay, let me scroll back down. Right. Okay, any other questions before moving on? So the other constraints are going to be defined in a similar fashion. Any questions about how this constraint works in terms of the table of the T's and courses that we had? Yes. That depends on the problem. Yes, yes. So if we went, in that case, we won't have that like enumerating all of the possible combinations between those two cases. For example, we will have only a 1D container containing the things that we're interested for, that we want to define variables for. And in that case, it would be simpler. Yeah. So that depends on the problem definition. Okay. All right. So the other constraint here, a TA can only be assigned to a course that they have listed as can teach or enthusiastic to teach. Okay, so the code kind of looks something like this. We have to retrieve something and then look inside of it to see if that exists or not. So this is the code for that. So we loop through all of the TAs and we loop through all of the courses and we say, if course not in that can teach list for that TA, and if it's not in that enthusiastic list for that TA, then we want to set it to 0 because we don't want to assign that TA to a course that they neither can teach or are interested in or enthusiastic about. So if they haven't listed that course, either in can teach or enthusiastic about, we don't want to assign that person. Okay, so there is. How about if I had stated this condition as whenever you see somebody's enthusiastic about a course, assign them to that course. Do you think that would also work? According to this constraint. Yeah, that might break the other constraints. And also the other thing is that based on the constraint, it says that a TA can only be assigned to a course that they can teach or enthusiastic about, but we don't want to necessarily do that. Okay, this is a possibility, but we don't want to. If you can't teach this course, I'm going to certainly assign you to that course. That's not the constraint. Yes. That's precisely true. Yes, yes. The constraints help us limit the search space. Yes. Yeah, so that constraint that we have to have 2 TAs per course, that is still in place, right? Because we have set that as a constraint. This is about how we distribute those TAs to the courses. So if they're neither like interested in teaching or enthusiastic about teaching, we don't want to assign them to that course. This is a different constraint. So yes, we still want to have 2 TAs per course, but I don't want those 2 TAs to be people who are not interested in this course. Oh, okay, so that doesn't matter. So as long as I have the most number of people enthusiastic in other courses, or maybe in this course, that's okay. That is still the optimal solution. The optimal solution doesn't guarantee that it can maximize everything. It is the best possible solution among the possible solutions. Yeah. Yes, for sure. I will show you that. Yes, definitely. Yes. Okay, so if we say course in TA or that. Yeah. Yeah, that's right. Yeah, that's an alternative way of doing this. Yes, yes. Yeah, it's from the set theory and stuff that you can do. Yeah, yeah. Yes. No, there's no order to the constraints. Yes. Oh, okay. We haven't yet defined the objective function. These are just the constraints. So the things that I want them to be satisfied for sure, but I haven't yet talked about like the measure that I have to measure happiness or enthusiasm. Yeah, we haven't done that yet. Okay. Yes. No, we are setting that to 0. Yes, we are setting that to 0. Because if they're not interested or enthusiastic, I don't want to assign them to that course. Yeah. No. Okay, that is not a variable assignment kind of thing. This is the way. So in regular Python, this would be a Boolean, but in this case, Pulp understands that this is actually an equation in math that you are expressing in this way. Okay, so that's the way that we have to. Just like in math, you say x1 plus x2 plus x3 equals 2. That equals should be denoted like that in code. Yeah. Yes. Uh-huh. Okay, wait. So if it's this or that. Oh yeah. Then yeah. That breaks the concept. That's right. So yeah, I guess we can. Yeah, that's right. We can express the AND condition with nots in a different form, but it won't work in this case. Yeah, thanks. Yeah, that's right. Yeah, because if I say this in that or in that, then I'm gonna have to assign that person, which wouldn't work. Okay, thanks. All right. So the other constraint. Okay, let's go through that a bit more quickly. So to cover a course, the TA must be available for one of the 2 lab days. And this is just a bit more coding, nothing really particular. So again, loop through all TAs, loop through all courses, and I'm going to look at here. So if the lab days of that course are not in the availabilities of that TA, and that's right, yeah. I'm just thinking about this index that I have here, and then, okay, TAs, DF availabilities. So for each course, we have this table over here. Okay. Yeah, we have this lab day, and then we have this. Okay, we have the course number and the location and the lab days, and then 0 or 1. Yeah, the code can be, I should have added a comment here for this. Yeah, so it achieves this, that the lab days should not, if they're not available in the availabilities of the TA in these two conditions, that we should set it to 0 because we don't want to assign that particular TA to that course. But just let me just inspect this to see what this actually represents. So for example, if I say 511 and query that, it says this, and Tuesday, but sometimes, yeah, okay, for Thursday that will be H. Okay, I see it. Yeah, this is what was confusing me. So I have to do something. Maybe I have to change the Thursdays to a single letter in order for this to work. But let's worry about that later. I think it still works in this case because my solution for both formulations look the same. Okay, so again, this is about whether those two availabilities that are listed, if they're not in the TA's availabilities, then obviously we don't want to use that TA because that TA is not available for that day. So again, just another condition. We add it to the problem object like this. We want to set it to 0 because the TA is not available for that course. Okay. Now comes the step where I define the objective function. Okay, and this is where the thing that you pointed out happens. So I want to maximize this sum of all of the x's where this enthusiastic ing is true, meaning that I want to sum over all of the TAs and courses, but only where the TAs are enthusiastic about those courses. So consider the table that we had with 120 variables, okay? And I want to consider all of those tables that are generated when the TAs that are assigned are actually enthusiastic about that course. Okay, and I want to sum them up and maximize that. Okay, so we can do this, LP sum. As soon as we have this form, writing the code shouldn't be that challenging. So LP sum, X over TAs and courses for, yeah, it's written in a list comprehension way. This form is more understandable. So for TA and TAs, for course and courses, if the course is in TAs underscore DF, meaning that if the course is enthusiastic for the particular TA, I'm gonna add it to that sum. So as soon as this combination of TA and course is something enthusiastic for that person, then I'm gonna add it to the scoring function, okay? All right, let me run this. And then, okay, I'm gonna come back to here. But right now, the definition of the problem is complete. So we have defined the constraints, we have defined the objective function, and the way that it understands that this is an objective function is because there is no double equal sign anywhere. So it means that this is not going to be equal to anything. This is free. We want to optimize it. This is free, okay? But the constraints are not free. We constrain them. Okay, so when everything is complete, we can call prob.solve, but if you do that, it prints out a lot of outputs that we're not interested in, so we can specify this argument here in order to suppress the output. Let's run that. 1 means that it was successful. And the status, we can check that out. It says optimal, meaning that what we have gotten is the best solution possible. And let's see how many enthusiastic courses we've got. So yeah, we've got 20 enthusiastic courses out of possible 24. Okay. Now, let me check the results here. Okay, this is per TA, so you can see that some TAs don't TA for all of the courses in the 3 blocks. Some TAs don't TA for any courses in that block, in all of the blocks, but that's fine. That's a solution still. Okay, and then here is the list of courses with their TAs. So we can, once we have this, we know that, okay, for these courses, if I assign these people, I have maximized the overall satisfaction between the TAs. Okay. And here are the enthusiastic courses. Okay, these people are enthusiastic about teaching those or TAing for those particular courses. Okay, so this, yeah, essentially that's it. These are a bunch of assert statements to see everything is fine, but other than that, yeah, that was the important thing here. So define the objective function and doing .solve. Okay, so in the remaining 3 to 4 minutes, questions. Let's see. Yes. A number of? No, we haven't. We haven't set the constraint for number of hours or like the language proficiency. No, in the real scenario we do that, but in this case, just for teaching purposes, no, it doesn't include that. Yeah. Yes, this is. I mean, we do something a little bit more complicated than that. So we also look at the proficiencies, the hours, and a bunch of other things. But essentially, this is actually it. Yeah, we do kind of the same thing for the capstone projects as well. Yeah. Yes. Okay. So the question is, if this guarantees the optimal solution, what was the? So if we have, because this problem is linear, if we have a space of feasible solutions, then yes, we can guarantee that what we get is the optimal solution. It may not be the only optimal solution, but it is definitely the optimal solution. This is only true for linear problems. It's not true for nonlinear problems. We will see instances of this in 572. Yes? Oh, usually, okay, I was going to show you an example of this, but I will do that in the lab. So sometimes the space of possibilities is limited or does not have an overlap. And in that case, what we get is a solution that might violate some of the constraints. So we say that that solution is not optimal. It's undefined for optimality, and it says infeasible. So in that case, yeah, we can say this. But otherwise, if there is a space to search over, because it's linear, we're going to definitely find the optimal solution there. Yeah. Maybe one other question. Go ahead.